Hey, we will continue solving the problems that we started in the lecture, and we have that example here. And in the previous part of that example, we found transfer function, controllability, and observability of our system. But now we also want to find transformation to the canonical controller form, and we want to find transformation to the canonical observer form, diagonal form if possible, and we want to write down these realizations of the system in different type of forms. So just to remind you that controllability matrix is given here, that we found previously, observability matrix is given here, transfer function of that system is given here, and to find transformation to canonical controller form, we need to use that type of representation. So we need to start with coefficients of the transfer function, and we can move it directly to that kind of thing, but we also can compute the transformation based on the formula. So let's write that formula. So T from the controllable state to canonical state will be equal to controllability matrix, which is matrix 1, 0.05, 0, 0.05, times that matrix. And that matrix is also 2 by 2, so it's starting with 1, and it continues with 1 on the main diagonal. On the bottom left you have 0, and here we need coefficient of a1. But what is a1? a1 is coefficient which is sitting here in the transfer function. So it's negative 0.1. This is that number here. Alright, so now we can compute that, and we will get matrix, which is 1, negative 0.05, 0, 0.05, and we define that as transform to a controller state. Now we will do the same thing with the transformation to canonical observer form. The transform will be like that. So here is the formula for the transform. So from observable state to canonical state will be equal to the following thing. In the formula we have that matrix first, and that matrix is very simple. We have 1s on the main diagonal, 0 above the main diagonal, and a1, which is negative 0.1 here. And then we multiply it by observability matrix, which is 1, 0, 0.05, 0.05, and inverse on all of that. Alright? So if you compute that, after a little bit of algebra, you will get the following matrix. It will be 0 here, 1 here, 1 and 20. And we define that as TO, which is conversion into canonical observer form. Now we need to get the actual realizations of the system, which are A, C, B, C, 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 which are controller state. And we know how they need to look like. So the actual matrices that we will get will look like that, or like that, or like that. And we can compute them directly, but I want to use T of C to compute them now. So let's see how it goes. So AC equals similarity transform that we found before, T of C inverse times of original A times of T transform C. And this will be as expected if you compute that 0.1, 0, 1, and 0. So if you're looking at the previous formula, this is exactly what you're supposed to get. So the coefficient here is negative 0, 1, so it's 0, 1, 1. A2 coefficient here is 0, free coefficient, and 0 here as well. Okay, so this is exactly what you get here, 0.1, 1, and 2 zeros. Same thing you're doing for matrix B. of C. So the matrix will be equal to T O inverse times B, and you expect to have 1 and 0. You can actually try to compute that and you'll have 1 and 0. And similarly for CO, C of C, controller, this is C T controller, and equal to 1 and negative 0.05, which are coefficients of the transfer function here. So it's 1 times z minus 0.05, so these are coefficients b1 and b2, so just copying them here. These are the coefficients. And you can actually test that this multiplication will give you exactly that answer. With observability is even simpler, because now you need AO, which is TO inverse 1, ATO, and this is just transpose of AC. So this will be equal to AC transpose. You have multiple ways to actually to get this, and this will be 0.1 and 0 here, but here we switch between 0 and 1. For BO, it will be equal to C transpose, which is taking that value and transposing it. So it will be 1, negative 0.05. And similarly for CO, this is B, C transpose, and this will be 1 and 0. You can verify all of that using simple computations, simple calculations, but now we want to get also to diagonal form. So to get diagonal form, we need actual roots of the denominator polynomial. So z squared minus 0.1z, this is our characteristic polynomial. This is z times z minus 0.1. So the roots are z equals to 0 and z equals to 0.1. So our function, transfer function, which is z minus 0.05 divided by z times z minus 0.1, could be written as something divided by z plus something divided by z minus 1, 0.1. So all we need to do is to find coefficients here and there, which will be equal to the original transfer function. So we just need to find them. Let's say you have coefficient a or alpha and beta, and you want to find such alpha and beta that will fit into that equation on the left. So now we do common denominator, so it will be again z minus 0.1, and here we will have alpha z minus 0.1 alpha plus beta z. So from here we have that alpha plus beta equals the coefficient of z, which is 1. Okay, this one plus this one. And also we have minus 0.1 alpha equals to minus 0.05, which means that this thing, transfer function, equals something divided by z plus something divided by z minus 0.1. While we can solve these equations, so alpha will be equal minus 0.05 divided by 0.1, so we'll get 0.5. And then we can substitute 0.5 into the first equation and get beta also equal to 0.5. All right. So our diagonal matrix AD will be equal all of the poles on the main diagonal, which is 0 and 0.1, and other than that it's all zeros. And now we have decision to make how we can make some coefficients, multiplication of coefficients of vector b and coefficients of vector c to give you 0.5 when they multiply each other. So let's say you can pick b of d equal to 1 and 1, and c of d equal to let's say 0.5, 0.5. You can also switch between them. The thing is that this one times this 0.5 should be equal to this 0.5. And this number times whatever this number is needs to equal to this number. And practically we've done with the diagonal representation. This is a presentation of the system in diagonal form. Thank you.